So Akshay is the director for modern technology at Mediatek. And today's talk will be focused on new innovations as proposed in 3GPP R17, R18. We will also talk about what are some of the key features that are currently being discussed for 6G and how they could make a significant impact on society. Mediatek's views on these features and their contributions to the standard bodies will also be discussed. Akshay got his bachelor's in electrical engineering from IIT Bombay, and then also did his master's in electrical computer engineering, and then he also has an MBA from UT Austin. So Akshay, very, very warm welcome, and over to you, please.
Thank you so much. Thank you, Slide. So today's topic is about beyond 5G. I've been working in Mediatek for the past, about 10 years, and my interest is modem technology and CPU. I've been working in 5G for the last 3 to 4 years, and our team has done a couple of chipsets in 5G. So I'll be talking about the different innovations that we've been working upon and what we can expect after 5G. So, before we do that, going to the next slide, which is big picture by the end of this decade, what we are seeing is that the number of devices that we can expect to get connected will be about 350 billion devices. That's much more than what we have right now. We are currently about 80 to 90 billion devices. But by the end of 2030, we can expect about 350 billion devices. And all these devices, they need to talk to each other. And because of which the total amount of traffic that can be generated is going to be more than 10 zettabytes per year. And this traffic has to be at a peak rate of about 1 terabits per second, with the energy conservation of about 0.1 nanojoules per bit. Because at such high data rate, if the energy is not conserved, the system is going to be very power inefficient. So to keep in mind this growth in number of devices and the traffic, it is extremely important that we are able to find technologies that can give us scalability beyond 5G. Currently, 5G is able to give us coverage, capacity, and bandwidth, but we still need technologies that can go way beyond that. And that's the motivation for us to look for technologies beyond 5G. Moving on to the next slide, which is titled Evolution Towards Beyond 5G or B5G 6G. It shows the trend that's happening right now. We started with 3G about 20 years ago and then moving on to 4G. Right now is the age of 5G where multiple devices are getting launched. So as we go from 3G to 5G, the data rate has increased from 10 megabits per second to a maximum of 10 gigabits per second. But still, that data rate is not enough. We need to go to about 1 terabits per second. At the same time, the MIMO capability of the devices have to increase from about 2 transmit, 4 receive in 5G to about 4 transmit and 8 receive in 6G. Similarly, the spectrum that is going to be used by these technologies has to keep increasing. For example, in 5G, the spectrum that was used was about 3 to 7 gigahertz, which is sub-6 band or the millimeter wave. But in 6G, the spectrum that's going to be used is about 7 to 24 gigahertz or sub-tera gigahertz. And the reason we want to go to this higher spectrum will be clear in the next few slides. But broadly speaking, as you go to higher frequencies, you are able to get more bandwidth and more capacity. Networks are going to become more dense. As I said, there are about 350 billion devices, which means in the same geographical footprint, you need to be able to support many, many more devices. And hence, the densification is going to increase. And of course, the million-dollar factor is the killer app. In 5G, the killer app was cloud gaming or extended reality. Of course, we're also talking about things like industrial IoT. But in 6G, it's going to be a notch higher, where we're going to talk about n-dimensional holographic communication. So this n-dimensional holographic communication is going to make virtual meetings much, much more beneficial. So what's going to happen is that if people are sitting far away in any part of the world, they're able to talk to each other and still see the face. And it looks like as if the meeting is happening in real time. Now, this concept could become very important, especially in the post-COVID era, when the remote working is going to become even more important. Of course, the another concept is AI efficient systems, which means the mobile systems, etc., have to be more AI efficient so that there is energy conservation and networks are more intelligent. Moving on to the next slide. So if you look at the driving trends and new KPIs for beyond 5G, 6G, clearly it's higher data rate, more reliability and shorter latency, flexible and smarter networking, and then AI to aid the integration of communications, computing, and control. So capacity, coverage, and energy efficiency are three important things. By service capacity, I mean to say the quality of service and the human perception for the service. The coverage should be accessible, affordable, and available. And lastly, but very importantly, energy efficiency, which means that the cost of sending this data, receiving this data should be very, very manageable at both the base station and at the UE. Moving on to the next slide, which is the tentative 6G vision. On the left, we see the popular 4G to 5G graph, which probably people have seen before. The inner light green circle is 4G, and the darker green circle is 5G. So the peak data rate increased from 1 gigabits per second to 20 gigabits per second in 5G. Similarly, the user experience data rate increased from 10 megabits per second to 1,000 megabits per second in 5G. Now, if you look at the right side, the peak data rate, which was about 20 gigabits per second in 5G, which is the inner white circle, is expected to go to about 1,000 gigabits per second in 6G, which is 1 terabits per second. Similarly, the spectrum efficiency is going to go by a factor of 2 times compared to 5G. And then the latency, which was about 1 milliseconds in 5G, is expected to go to about 0.1 milliseconds, which will make all the holograms, extended reality, all those concepts much more realizable. Moving on to the next slide, this just shows the frequency which is available for new use case scenarios. For example, if somebody has to do an immersive extended reality, the bandwidth that is required is about 20 gigahertz. Now, how do you get this high bandwidth? You could refarm legacy cellular systems, you could share unlicensed spectrums, or you could explore higher spectrums. So smarter carrier aggregation, smarter spectrum sharing, and new 5 techniques for terahertz are all important concepts that can be used to get this higher frequency data. Moving on to the next slide, which is spectrum ranges. So spectrum is a very, very important commodity, and what we have to see is how we can harness the limited spectrum that we have for 5G and then for 6G. So on the left side, what we see are concentric rings. What we are trying to show is that at the lowest rung of the ladder, or the lowest band, which is about less than 1 gigahertz, those frequencies are very good for coverage, but they're not good for capacity, and they're not good for higher speeds. As you move from low to mid to high to ultra high, you're going to go in higher frequency ranges, and at the same time, they offer much more capacity and much more bandwidth. So for 6G, where we require higher speeds and higher bandwidth, but at the same time good coverage, what we are looking for are the mid bands, which are about 7 to 24 gigahertz range. And at the same time, we are also looking for the sub-terahertz frequencies, which are about 71 to 300 gigahertz. So terahertz is actually 300 gigahertz and above, but anything below 300 gigahertz is sub-terahertz. So those are the range of frequencies that we'll be looking for in 6G. Moving to the next slide, which is titled Spectrum. So this is pretty much a rehash of the previous slide. What we are showing is that beyond 7 gigahertz or in sub-terahertz, the opportunity is there for large amounts of new spectrum. And there is also the possibility of spectrum sharing by coexisting with incumbents and also sharing with incumbents. So there are a lot of different spectrum options that can be tried out in 6G. But the key idea is that we have to move to higher frequencies for TDD networks. Moving on to the next slide for timeline considerations. So this picture shows basically how it's going to progress as we go from 2021 all the way to 2030, which is IMT 2030, is also 6G. So currently, all the mobile devices that are available are Release 15, Release 16 compliant. And as we speak, Release 17 is going to get finalized in the next 3 months. Sorry. And then Release 18 is going to get started. So at the bottom of the slides, I'm talking about some of the key points in Release 17 and how they realize the beyond 5G vision. For example, IAB technology, which is integrated access and backhaul, is an important concept in Release 17, where the idea is that all the rural areas where there's not enough fiber, you could use the spectrum which is allocated for access also for backhaul to give the connectivity. So you don't need any fiber in that area. Also, things like NTN networks, which are the non-terrestrial networks, are a key feature of Release 17. As we go to Release 17 to Release 18, which is the first version of 5G Advanced, there'll be AI and ML over air interfaces, MIMO enhancements. RedCap devices are an important concept, which are reduced capability devices. And then the terrestrial network and non-terrestrial networks are further going to get optimized in Release 18. So all this will help us in realizing our vision for 6G. Going on to the next slide, which is titled Radio Characteristics of Terahertz Waves. So we've been saying that we want higher frequencies, sub-terahertz frequencies, but what one should also realize is that as you go higher in the carrier frequencies from about sub 1 gigahertz all the way to 100 gigahertz and above, the y-axis, which is the attenuation, increases. And that attenuation increases as the carrier frequency keeps increasing. So just as a case in point, there's an additional path loss of about 15 dB at 140 gigahertz compared to about 1 megahertz. Now this 15 dB of loss somehow has to be compensated for to make the technology success. And that's a challenge that we have to overcome. So moving on to the next slide is SOC, which is the practical 6G technology principles. Mediatek believes in the principle of simplicity, optimization, and convergence. Simplicity is basically sustainable improvement under simplicity principle, which means no compromise on energy efficiency, use the traditional designs, and enable them for high performance. Optimization basically means that what we have to do is we have to make sure that the design is very much optimized and there is artificial intelligence and machine learning going on. So those are the important things. And convergence basically means there is a convergence of terrestrial and satellite access. So these three things are pretty important concepts of the design. Can we move to the next slide, please? So convergence of communications, computing, and control is happening. The G node B is talking to the UE, which basically means that there is more and more number of devices which are energy efficient, and the edge is moving closer to the UE, which means there's edge computing for latency reduction. And thirdly, but most importantly, is the cloud, which is going to be closer to the UE and the edge for XR and cloud computing. This will help in better QoS and enable more and more data rates to be given at a much higher frequency. The energy footprint and power efficiency has to continue to improve, and this will happen when there's network densification without increasing the energy footprint. It means energy-aware end-to-end service delivery, and there's a concept of hybrid network with hybrid nodes. And the devices can be switched on and off as per requirement to save power in the network and the devices. So this also enables big little modem architecture, which could help us in saving some power. And moving on to the next slide, which is the heterogeneous network deployment for sub-terahertz communication systems. So what we have to do is to make sure that the path loss can be optimized. It's important that the repeaters and the UE-based relay systems, IOB nodes, and RIS systems are inserted between the base station and the NUE to make sure that the path loss can be compensated. And by doing this, what we can make sure is that the sub-terahertz frequencies have similar or lower path loss compared to sub-6 gigahertz frequencies. Moving on to the next slide, which is the distributed network architecture and side link. What we're trying to show over here is that in 6G, there'll be a lot of device-to-device operation, which is the side link. And this... Hello? Hello? Yes. So I'm on slide number 15, which is distributed network architecture and side link. And that's slide 15, distributed network architecture and side link. So we have the device-to-device operation happening over there, which is the side link operation between the device, all kinds of devices that are sitting in the network. And these devices can also talk to the base stations, and the base stations can then relay back to the nodes and to the devices on which particular technology and which particular device has to relay. By using this kind of a mesh architecture, what happens is that you are able to save power, and even though the network is getting dense, but the devices play a very important role in this kind of an architecture. Moving on to the next slide, slide 16, which is further enhanced coverage, AI for beyond 5G and beyond 5G for AI. Now, AI is going to be an extremely important concept in the future networks. What you see on the bottom side, which is the yellow part, is the communication network that we have right now, which is the core network, the RAN node, and the G node B and UE. That's the traditional network that we have right now for 4G, 5G, 3G. On top of that, there's going to be an application layer sitting, and in this application layer, you're going to have a communication-aware application, which is the all these applications are actually AI-driven, and these applications learn from each other. At the same time, these applications are exchanging information with the core network below. And then that core network is sending data back to the application layer, and the application layer is using that information to feed back some data back to the core network. And this back and forth can help in optimizing the network, which is currently existing. At the same time, the UEs are talking to G node B to minimize the data and the signaling compression. And by minimizing the compression, they're able to save energy, and they're able to save resources for more and more data transmission. Moving on to slide number 17, which is how AI and ML works. So basically, it shows 4 models at the bottom. The leftmost model is where the AI is running on the network side with a pre-trained model. And in this, what's happening is the base station is going to give some command to the UE, and the UE is giving the information back to the base station to improve the model. As we progress from left to right, there are different variations of this model. And on the rightmost side is the extreme, where both the base station and the UE are trying to infer the information that they get from each other and train their own AI models. And that's called collaborative AI or federated learning with joint training. That's the ultimate goal, where the network and the devices and the base station are continuously evolving to get better and better. Moving on to the next slide, where I show some AI and ML implementation examples for beyond 5G. A couple of things over here, for example, channel characteristics. DMRS is some information which is typically sent from the base station to the UE to help decode the data. So with AI, the DMRS estimation can become better, and because of which you're able to decode the data faster. At the same time, CSI, RS overhead reduction. CSI is the channel signaling conditions as the G node B is transmitting data to the UE. So this is the downlink channel conditions. And similarly, there's an SRS, which is the uplink channel conditions. So currently,
more questions coming by. So basically, one of the questions is more, I would say, around the financial aspect. The question specifically is, what are the financial implications of rolling out 6G after 5G? That's the specific question.
Yeah. Again, very good question. So, the thing is with 6G, because the frequencies are going to be very higher, so and at a higher frequency, there's much more loss, which means you'll have to have more and more number of base stations in the same cell area. Now, if you're going to use that same dumb approach of putting more base stations in the same cell, means it's going to be much more costly. Similarly, if you don't do any power optimizations, the base stations are going to burn much more heat. The mobile phones are going to burn much more heat, which means you need to have very expensive cooling mechanisms. So if you don't do anything, the financial impact is going to be very, very large. Because of which, the network operators, the infrastructure vendors, and the device vendors have to work together. For example, you can't just rely on the base stations to be the networks. As I said, hybrid nodes or the devices also being a part of the network is going to be important. Which means we don't increase the number of base stations, number one. Number two, all the base stations and devices don't have to be on all the time, which means you can decrease the power consumption of the network. So these two examples can basically help you to decrease the number of devices and also at the same time decrease the energy consumption of the network, which can again lead to simplistic designs and hence not so much of a financial impact. Now, one good thing also I would like to say is, as you go to higher frequencies, luckily the spectrum is readily available, so the large cost of acquiring the spectrum is taken away. Up to 6 gigahertz or 5 gigahertz, a spectrum is very expensive, but beyond that, the pricing falls down. So for the operators, that particular saving is going to be there, that they don't have to spend obscene amount of money to get a 6G spectrum. Yeah.
Thank you. See, the next question is, you talked about the convergence between LEO and GEO. So there is this aspect of 6G actually delivering a lot of power and energy savings as a technology. So when we attempt this convergence, do we see loss in the power gain or the advantage that has been gained by 6G? That's the question.
Okay, so I think these are little different concepts. The LEO GEO and first of all, LEO GEO are these NTN, are these satellites which will help you in non-terrestrial network communication, and they are going to actually work closely with the terrestrial networks. The power that is going to be beamed to these NTN satellites, or the power that is going to be beamed from the NTN satellites back to the terrestrial networks, is going to be under control. So that power consumption is not going to be the big bottleneck. Over there, the big bottleneck is going to be, managing the delay and the round-trip delay between the NTN networks and the terrestrial networks. The power consumption game is going to mostly happen on the terrestrial networks, or I would say the picture is same for terrestrial networks or non-terrestrial networks. As I said in a couple of minutes ago, we have to be very much cognizant of the fact that there are more and more number of devices, which means all the devices can't be turned on at the same time, else we'll be wasting a lot of power. Similarly, the signaling that's going to happen between the UE and the base station has to decrease so that power savings can be there. And thirdly, and most importantly, what we have to make sure is that the power that is radiated from the antenna can be controlled by having some relay nodes in between to compensate for the path loss. So I think those are some generic techniques to reduce the power consumption, and they can be applicable both for terrestrial and non-terrestrial networks. So the convergence I was talking about was for terrestrial and non-terrestrial networks, but the power consumption concepts are similar for both TN and NT networks.
Thank you, Akshay, for clarifying. Yeah. We are on the clock, but we have 2 more questions, so if you're okay to take those.
Sure.
Okay.
Yes,
The
please.
next question is related to the answer that you just gave, which was you mentioned that
Yeah.
Mediatek has a device which you've used to, basically experiment this convergence between or validate the NTN and TN.
Yes.
And is that a commercially available device? Is the question. And also, you also mentioned a chip that Mediatek has designed. So these are the two questions.
Yeah. So this particular chip or this particular product is being productized as we talk. And this is going to be used for the NB-IoT applications, and which is going to harmonize both TN and NTN networks. So yes, it's there. So this was a proof of concept that we had given about 2 years ago, and now we are productizing it. So yes, it's available.
Thank you. The next question is around with the new evolution of technology with 6G, what is the scope for the electronic systems design and manufacturing industry scope, meaning the opportunity that you see?
I think there's a lot of opportunity out there, especially coming from a chip design company. I would say like Mediatek, which focuses on designing those SoCs which are going to go for mobile communication. I think we need a lot of help from the budding engineers, from experienced engineers, to see how we can make those things happen. For example, CMOS is the technology is the technology of choice for making devices for 5G, 4G, but they have their own FT/Fmax constraints, which are about 300 gigahertz, and which is simply not sufficient to meet the 1 terabits per second requirement that we have from 6G. The other device types, which are SiGe or GaAs, which are good devices, but they're not really that commercially viable. So device is going to be a very important part of 6G. Similarly, antenna selection, substrate selection, those are very important part because the substrate has to be as less lossy as possible. And how do we pack more and more number of antennas in the same chip to be able to transmit the network, to be able to transmit the power? So chip technology, antennas, passives is going to become very important. Similarly, software is going to become very important because how do you optimize that and artificial intelligence layer so that the network can become self-organized? How do you make the network heterogeneous? So the software skills is going to be extremely important. So I think the innovation has to be kicked to a next level if we were to see 6G become a reality in the next 5 to 7 years. So definitely we need a lot of help from the IESA industry and engineers.
Thank you, Akshay. One last question before we wrap up. If
Sure.
there were two things that you would see that would catalyze this adoption of 6G, maybe even faster than the 5 to 7 years, what would those be?
Yeah. Okay. I think in my opinion, there are two things which are going to be, the catalyst for 6G, which I said in the beginning, the killer use case. One is, I would say, applications which are very latency sensitive, and when I say latency, which means device to device delay sensitive. So autonomous driving, remote surgeries, or industrial automation, where it's very important for the network to talk to the devices ASAP. For example, there's something called a new technology coming as CV2X, where vehicle to everything. So if that trend picks up, where it's extremely imperative that the delay between two devices or the lag between two devices is minimal, 6G is going to become very important, number one. Number two is anything which is bandwidth intensive, like I was talking about this XR games or XR kind of applications, especially holographics. So as I said, in the post-COVID era, where it might be difficult for people to be coming to office all the time, but at the same time, you want to see people's emotions in meetings. I think holographics can be an extremely key technology where you could have a real meeting-like environment without the people being present there. So the catalyst for that could be if the companies, if the organizations promote that kind of behavior where people are working remotely and yet you don't lose the benefits of face-to-face meetings. So for me, I think those are the two key things which I see as catalysts for this new technology.
All right. Thank you, Akshay, for that, very comprehensive presentation. And also thank you to the colleagues, your colleagues who helped you put that presentation together. I know we did start the session about 10 minutes late than expected, but I think you pretty much made up for it with the excellent presentation. Also, I would like to thank all the attendees who have been patient and who stayed on the line in spite of the delay. So also, I think, Akshay, the future that you've painted for 6G and what is possible and the areas of innovation, both for the carriers and the ESDM industry, is definitely heartwarming. And also, we do look forward to the development that Mediatek is making as far as devices